Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing tree topic and pattern was DFS traversal. We have already saw what is DFS traversal and what is BFS traversal in our previous videos. I'll attach the link somewhere here. You can check that out. And now we'll start solving the questions using both traversal, means with DFS also and with BFS also. So let's read the problem statement. The problem says we will be given the root of two trees and we have to check if they are same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. It means their structure should be same, means left. If there is a left child for tree 1, there should be the left child for tree 2 as well. And if they both exist also, their values should be same. Otherwise, they will not be identical. Okay. Now let's read the constraint. Constraint says the number of nodes can be 0 also. It means we have to write the base case. Okay. And the maximum number of nodes can be 100. It is very small. Okay. And the node values can go from minus 10,000 to 10,000. Why we read constraint? Because it helps us to check ki do we need integer or long? Do we need to write the base case or not? Will our code give TLE? Means do we need to optimize it or not? So after reading the constraint, we are pretty much sure ki O of n square, all code will work here. Why? Because the constraint is very small, 100. So O of n square, n cube, all will be smaller only, means less than 10 power 8. Because beyond that, it gives TLE. How we know that? Because we have discussed all of these things regarding the time and space complexity in our full YouTube video. I'll attach the link somewhere here. Now, let's try to understand the same tree concept. So the question is very simple. I can say they are same tree if they have root same, done. Value same, done. Left child, yes, exist. Value same, yes. Left child exist, yes. Value same, yes. Okay. Right child exist, yes. Value same, yes. Similarly, right child exist, yes. Value same, yes. So can I say this is same tree? I can say, okay, this is same tree. Now let's check for the second one. Nodes same, value same. Nodes same, value same. Left, value same. Right, exist, yes. Value is not same. Okay, done. Means this is not a same tree. So whatever we discussed, can we write the cases here, base cases here? Very simple. What I saw, see here for 3, it does not have left child. Okay. This also does not have left child. It means, can I say if both roots are null? Means true, like we can return true from there. Can I say that? Yes. So what we need to do, I can write one thing for sure. Whatever I am recognizing, I want to write this. If root 1 is equal to null and root 2 also null, I can say, hey, yes, you are same tree. It means कि when both were null, we don't need to check na कि values are there or not, because both are null. I can say yes, it is same tree. Now the thing is, here in this tree, what we have found कि both existed, but their values were not same. Their values were not same. Okay. So can I say कि if root not is equal to null and if root 1 and root 2 not is equal to null. Okay, if both exist and if root 1 dot value, okay, not is equal to root 2 dot value, can I say return false? Return false. Why I said this? See, I said both exist and their values are not same. Here also both existed and their values were not same. So can I return false? Done. Now let's see example number 3. Okay. Root 1, done. Left, yes. Value same, yes. Root 1 dot left exist. Value same, yes. Root 1 dot right exist. Root 2 dot right does not exist. Means can I say, now when we called this root 2 dot left, we sent this in function root 1 dot left and root 2 dot left. Now root 1 and root 2 has become the new values. Means root 1 is 5, root 2 is null. So can I say if root 1 is not null and root 2 is null, return false? Vice versa also. See, root 1 is null, but root 2 is not null. Means if both were null in this case, then to it was true. Or else, if we can say ki any one is not null and other one is null. Any one is not null, other one is null means false. Correct? So we'll write ki if my root 1 is equal to null or root 2 is equal to null. Okay, why I write this in return false? Just wait a second, return false. Okay, why I have wrote this with using the OR operator? See, if this has not passed, think again, this has not passed, it means for sure ki either both exist or any one exist. Means if both were null, this would have passed and it would have returned true. But if this condition, this if case does not passes, it means either both are not null or else if any one is not null and other one is null. Can I say this? So for the second check, if any one is null, or means if root 1 is null, it will return say, hey, root 1 is null, but this does not pass. For sure root 2 was not null, then only it does not pass, right? So if root 1 is null, it means root 2 is not null, for sure return false. Or else if root 1 is not null and it says root 2 is null, because OR condition what it does, OR condition says ki if first will pass, I will not check the second one. But if first said ki no, it is not null, then it will go for the second check. And if it says it is null, means for sure root 1 exists, root 2 does not exist. It means that condition passes na, ki one exists and other does not exist, means return false then and there. Done. Okay. Now the third one, if this line does not passes, this line does not passes, it means for sure what? Both exist. Can I say? So do we need to write this check? I don't think so. Yes. Correct. So if we are at third check, for sure this does not pass, this does not pass, it means both exist. And now if both exist and their value does not matches, return false. Done. Now what is the fourth condition? Both exist and their value also matches. See, when both existed, value also matched. What we did? We went for left call, we went for left call. We went for right call, we went for right call. That's what we are expected to do. Now the thing comes, ki how do you want to traverse? Means when we are done with the root check, now it's children's time. And when it comes to children, we know there are two traversals and that we have learnt, DFS and BFS. So if you want to do with DFS, means we have to call a function. And we want, in every function we want root 1 also, root 2 also. So can I say our function was something like in DFS, we have root 1 also, and in DFS we have root 2 also as parameter. So now when we have to call for left, now when we have to call for right, what we will send? We will call the same function, very good, root 1 dot left. Can I say why this? And what along with root 1 dot left, why? See, when we were at 1, okay, root 1 dot left we want to send and root 2 dot left we want to send. Why? Because we want to check if this 2 and this 2 are same as a node also and the value also. Correct? So in the left function call, we have to send both together. And similarly for right function also, root 1 dot right and root 2 dot right together. Because now we want to check if 3 exists and if their values are also same. Can I say that? So here what we will say, DFS, root 1 dot right we will send, root 2 dot right we will send. Done. Now think again. And the condition is, suppose these tree does not exist. Suppose this much does not exist. We were at 1, we called for this and it matches, it will return true. Then again we called for this also matches and this also return true. Means from left also it returned true, from right also it returned true. Left true, right true. So is it like we have to return true if any of these return true, or we have to return true when both returns true? Think again. Means what if this was not 3 and this was 4? Then though for sure the right call would have returned false. means one returns true, other returns false. So can we say these are same tree? No, na. Means both should be true. Tree means tree left side and tree right side. So what should we actually return at the end after the call? Yes, return left and right. Can I say? If both are true, then only and will pass and it will return true. If any of these one or both are false, okay, false, true, or else true, false, or else false, false, this will return false, and that's what expected. So this will be our DFS call. DFS call. Okay. Now let's see their stack calls. Okay. Let me erase first of all any one of these. Okay. Now this is our stack. Here we'll save all our calls. First in DFS, what we sent? DFS, like let's say function, we sent root 1 as 1, root 2 as 1. Okay. Now we went for left call. We went for left call. Function root 1 dot left, which is 2, root 2 dot left, which is 2. Again for DFS, left call. Root 1 dot left means 2 dot left. Function 4, 4. Again for 4 dot left, we'll call it. Function 4 dot left means null, null. Both are null. So now in the function it will check root 1 is null, yes. Root 2 is null, yes. Return true. Okay. So this will be rolled out and it will return true to its parent. True. What was this call? Can I say it was 4 dot left call? Now similarly we'll go for 4 dot left right call. We'll again do null, null. Again this will return true. Correct? So this left also return true, right also return true. So at the end what was expected? Left and right. So 4 will return true to its parent, 2. Okay. Now it's time for 2 dot right. So for 2 dot right, like 4 has returned, right? So we will remove from the stack also. Okay. Done. So 2 dot left will also get erased. Now we'll go for right. 2 dot right call. Now function will have 5, 5. Okay. 5, 5. Again both matches? Yes. Now for this again we'll go for left call, which is again it will say function null, null. This will say return true. Okay. Now 5 will go for right call, function null, null. Both will say yes, return true. So for 5, left side also return true, right side also return true. So left and right, 5 will return true to its parent. True. Done. Now again for 2, like 5 will get removed from the stack call. Done. Okay, done. Now for 2, 5 was the right call also, na? So left also done, right also done. So for 2, left is true, right is true. So what it will return? True. So 2 will return true to its left and it will get removed from our stack call. Now we will call for 1 dot right. 1 dot right. For 1 dot right, function 3, 3. Now suppose this was not 3. Suppose this was not 3 and this was 4. Then it will go and check exist here in this call. Both exist? Yes, both exist, but their values are not same. So it will return false. Okay. So it will return false. So for 1, left says true, right says false. So in total it will return false. And when it will return false, after 3 removal, 1 will also get removed. Stack will become empty and we will get false as an answer. So the space complexity was, we have inserted every nodes in our stack. So O of n, done. And time complexity, again we have iterated to all the nodes at one time. Okay. So time complexity and space complexity both will be O of n for this case, means using the DFS traversal. Okay. So can we write the code for this? Okay. So here we have P and Q. So our task is to first check the base cases. If our P is null and along with that Q is also null. Remember, if both are null, then we can say return true. Return true. Okay. Now, if any one of these are null, means or. For sure, if any one of these is null, means second one is not null. So in that case, return false. Done. Or else, now we have to check for the value. Correct? Remember? So we have to check if P dot value does not matches with q dot value, it means we have to return false. Otherwise, what is the condition? Otherwise, call these left and right. So can I say I'll call the is the same tree? There are two ways, okay? There are two ways means in the Boolean format, let's say left, save your call means p dot left, q dot left, done. Similarly, in the Boolean format, right is equal to is same tree. Now p dot right, comma q dot right. That's it. And now at the end return left and right. Correct? Or else you could have returned by just calling these two functions with the left and right. Okay? In place of left and right. So let's run the code. Done. Now let's try to submit this. Done. So O of n, time and space complexity for this. So this was a code in Java. Here is the same code in C++, and here is a similar code for Python if you are from Python background. So this was the DFS traversal code. In the next video we will discuss BFS traversal also, but as of now we have solved this question. So let's go in the sheet and let's mark the next question also done. Now we have one more question with a similar concept, and that is symmetric tree. So let's read that problem statement as well. So guys, here is a problem statement. It says we will be given one binary tree and our task is to check if they are symmetric or not. Symmetric means we can say mirror image. It means one's left child should be matched with one's right child. If you can see here, for 1, 2 is a left child and 2 is a right child. So they should match. Okay. Now again from 2 onwards, you can consider this 2 trees, correct? So for 2 dot left, for the left side, here you can see the 2 dot left means this 3 should match with another 2 dot right, okay, because these are mirror image. So left child should match with the right child, okay. So if the conditions are true, you have to return true or else false. Now why I said this is similar to our same tree, I'll let you know soon, but let's go and check for the constraint. It says the number of nodes will be 1. So if you are doing with like this question with the BFS approach where you put all the nodes in the queue, you don't need to check for the base case key. What if root does not exist? Because minimum number of nodes have been given. But in DFS call we have to write. Why? Because the base case, which is if root is null return, that is the only condition to stop our recursive call. So hence in DFS we always write the base case, but in BFS if number of nodes are not 0, then we can skip writing the base case also. Okay. So now let's go and try to understand this problem. Now here I am going to take the same example for the symmetric tree, and the idea is very simple. If root matches, okay, now its left should match with the right, means this should be 2, okay, this should be 3. Now we can say yes, 1 dot left and 1 dot right matches. 1 dot right and 1 dot left matches, yes. Now for this case 2 dot left is 4, but 2 dot right is not 4. So now we can return false. But if you want the exact symmetric tree, this is how it will look like, 4. Okay. So in the calls, when you will send for 1 dot left, 1 dot right, in the next stack it will be root 1 and this will be root 2. So for root 1 dot left, you have to check root 2 dot right. Okay. Isn't it similar? Again, all the cases, base cases will be same, means for 2 dot, like there the only condition was ki for 2 left there should be 2 left, but here we are checking for 2 left there should be 2 right. Can I say that? So if 2 dot left is there but 2 dot right is not there, suppose it is null, return false. If 3 dot left is not there, 3 dot right is also not there, both are null, return true, because this is the condition, true condition, correct? Means if both are null, return true. Can I say the same case? If both are null, return true. Now the other one is if one is null, suppose let's add this here 5, okay? So if one is null and other exist, return false. Means second case also matches, done. Now the other condition, if both exist, but their values does not match. Suppose it is 5, this is 4, values does not match. return false. Same condition. Value does not match, return false. All things are same only. Then what is the difference? The difference is when you have matched the first root and you called for the second one next time, in the same tree you will call for root 1 dot left, root 2 dot left. Remember, in the symmetric tree, for root 1 dot left you have to match with root 2 dot right, not with left. Means in same tree root 1 dot left, root 2 dot left, but in the symmetric tree root 1 dot left matched with root 2 dot right. Similarly, root 1 dot right matched with root 2 dot left, and that's it. Yes. So basically I just showed you that this left right do not need to store. Okay, we can simply add in the return statement ki return either this call and this call, but with root 1 dot left root 2 dot right will go, and with root 1 dot right root 2 dot left will go, and that's it. Yes, yes. And now all the dry run will be like the stack dry run will be same as it is. Let's do it for you. Initially what will go? Function, this one and this one. But wait, if you check, if you saw, the tree was same. Like you will be given just one tree. 1. Now this is 2, this is 2, this is 3, this is 3, this is 4 suppose. Now you have to check this. So root will be 1 only. So you have two options. The thing is, key make your symmetric call. Like function you have to make, and the function send root as root 1 and send root as root 2. But going forward, root 1 dot left, root 2 dot right, it will consider. But both root 1 and root 2 are the same only. What I said, make your own function and send root 1, root 2. Okay, and write all the conditions here what we discussed. But when you are calling this DFS function, send root. Okay, so this will consider root 1 and this will consider root 2. Next time when you will call for root 1 dot left, you are actually calling the same root, but this will happen only for the first time. Next time this will become root 1, this will become root 2. So next time this left and it's right. Okay, so let's save this in stack. So in the function it will be 1 1. Now for 1 dot left, what you will call? Root 1 dot left, function 2, and root 2 dot right, function 2. Now this was left call, right? Now what will happen? You will call for 2 dot left and 2 dot right. So function 2 dot left means 3, 2 dot right means 3. Again for 3, you will go for left call. So it will say null, null. Both are null. So when both are null, you will return true. So this will return true. Its right will also return true. True, true. Both are true. So this will return true. 2 it's 2. So this will get erased and 3 will also get removed. And 3 will return true to its parent. Now 2 will call for its right side. 2 will call for its right side, which means 4. Now root 1 dot right, but root 2 dot left. It says I exist, but I does not exist. Means from 2's right side, this will return false. Okay, from false. So 2 will also get removed. So in total, it got true from left side and false from right side. So AND operator on this will get returned false as the final answer. So 1 will also get removed from here, and that's it. So the time complexity is, can I say O of n by 2? Exactly. It's linear only, n only, but it's n by 2. Why I said? Because the same tree you are checking now. So this node and this node together you are sending in the same function. This node and this node together you are sending in the same function call. So in total, time and space complexity will be n by 2 exactly, which is linear only, which is O of n. So you can say that in the interview, it is O of n, which is linear. Okay. So the only line of code which we have to change is this part and this part. That's it. Means we have to swap it. Okay. So can we write the code? So let's write the code. First, we will make a private boolean function. Private boolean. We have to check is mirror. Symmetric means mirror only. Okay. So let's name the limit, and type will be tree node. We will get root 1, and tree node we will get root 2. Done. Okay. Now we will bring this much line of code. Okay. Here. Okay. But we have PQ now, so let's name it P and let's name it Q. And now we have to swap Q dot right and here Q dot left for mirror. Can I say that? Okay, now here we'll check if our root is null, the very first base case, what if root does not exist, then to return true then and there, no need to go for the mirror check, or else return whatever the is mirror function is returning with p and q, and p and q is nothing but root, that's it, right? Now let's run the code. Okay, my bad, sorry, is mirror, we have to swap both of these functions, I forgot. Okay, now let's run this and done. Now let's try to submit this. Done. So this was the code in Java. I hope you understand. And what change in code has helped us to submit this? So here is a C++ code with a similar approach, and here is our Python code with a similar approach if you're from Python background. So that's it. With this we can go in the sheet and mark the next question, which is symmetric tree, as done. So if you understood, give a thumbs up in the video and make sure you subscribe the channel if not yet subscribed, and also do let me know in the comment section if you like the approach of teaching the similar problems. So this was a DFS approach, guys. In the next video we will discuss the same problem, same two problems, but with the BFS approach. Why? Because so that you will learn how can we solve the questions with both approaches, means DFS and BFS. So if you like the way of teaching and the pattern wise recognition, let me know in the comment section, and make sure to subscribe and share the channel with your friends. And if you want the sheet link, and in case you want to connect with me on social media, all the links you will get in the description. That's it for this video. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.